The next two colligative properties I want to talk about together, and you can see a little bit of a preview of what we're going to look at, which is the phase diagram for something to illustrate how and why these properties change as you put solute into the solution. So if we just think about our definition for boiling point, if you remember from an earlier chapter, the boiling point was when we get the vapor pressure to equal the external pressure. So what happens when you have a solution is that the solute, which we actually just did this calculation, the presence of the solute lowers the vapor pressure. So because that happens, we have to heat the solution to a higher temperature to get the vapor pressure to equal the external pressure. Okay, so on this phase diagram for water, I'm going to add a second set of lines. So everything that is here in the black lines is for the pure solvent. And I'm going to use blue to draw what you would see for a solution. Now the amount by which these lines go down depends on how many particles you put in solution. This blue line is for the solution. So what we can do is we got all of our normal boiling and freezing values by taking our 1 atmosphere line. Let's do this. Yes, let's do it in gray. And carrying it all the way across, right? Because those are our normal conditions. So anywhere the liquid gas line crossed 1 atmosphere, that was our normal boiling temperature. So this, I'm going to put it down here as TB with little 0. And it's already marked at 100 degrees, which we know to be true. But if we look at where our solution line hits 1 atmosphere, and we drop this down to the temperature axis, this is the boiling temperature of the solution. Our delta TB, I'm going to mark on here because this is technically what we're going to end up calculating. The new boiling temperature is at a higher temperature. If we do the same for the freezing point, our new freezing temperature, we mark our pure freezing temperature first, and then our new freezing temperature, we've got a delta TF. Our freezing temperature for the solution is lower than the freezing temperature for the pure solvent. So I'm going to give you these equations. We are technically going to calculate delta TB and delta TF, and then you will be responsible for remembering to increase your boiling temperature and decrease your freezing temperature. All right, so for these equations, we finally get to use my favorite concentration unit, which is molality. And these equations look like delta TB equals I KB, which is the boiling point constant, times the molality of the solute. So this time we're using the solute, not the solvent, for the concentration. And delta TF is I times KF, which is the freezing point constant, also times the molality of the solute. So KB and KF, these are the boiling and freezing point constants. These will be given in the problem, or you will be told where to look them up. They're not collected in a very nice place in the appendix like some of our other values. These depend on the solvent. So there will be a value for water. There will be a value for any other liquid that you could possibly use as a solvent. So I do have one example that we're going to do for this. So I'm going to pause the video, I'll write it out, and then we'll come back and look at it. This example says a solution is prepared by dissolving 1.7 moles of ethylene glycol in 1 liter of water, which has a density of 1 gram per mil. Calculate its boiling and freezing points, and then we're given the boiling and freezing point constants. Something that I didn't get put in here, but you will need to know to solve the problem, is that ethylene glycol is a non-electrolyte. So it is soluble, but it is a non-electrolyte. So we need first the molality of the solute. So we need moles of solute over kilograms of solvent. Okay, so we just have to do a couple of unit conversions. Actually, once we write it out, it's going to feel a little bit silly, but our 1 liter of water, I'm going to start, technically, I did a unit conversion here. It's the same as 1,000 mils, and I did that because we have our density in grams per mil. So the mils will cancel out, we'll be in grams, but we actually need to be in kilograms, and 1 kilogram is 1,000 grams. So, okay, well, our 1 liter is actually just 1 kilogram of water. So our molality is 1.7 moles of solute in 1 kilogram of water. So our molality is 1.7. So calculating change in boiling and freezing point. So my delta TB, the I factor, it's a non-electrolyte. So my I factor is 1 times the boiling point constant, which is 0.512 degrees C per molal, times the molality, which is 1.7. So my delta TB is 0.87 degrees Celsius. But the problem asks for the actual new boiling point. So my new boiling point is whatever my original boiling point was plus the amount that it went up. So my new boiling point is 100.87 degrees C. And for freezing point, my delta TF, I factor is 1. My constant is 1.86 degrees C per molal times 1.7 molal for the concentration. And you get 3.2 degrees, but the freezing point is lowered. So my new freezing point is 0 minus 3.2. So my new freezing point is negative 3.2 degrees C.